Questions about anything at all? I also graded your homework too. I had feedback typed up in a file because all of you were doing your homework on Excel, and then apparently I did not send it to myself from home. So I'll get that to you on Wednesday. Thought I had sent it to myself. Got here. It wasn't here. So, all right. So one of the reasons why I sent you the file of data that I sent, it's just different. There's different problems that were in the book that have different data in it that are a lot of data. So I just had one of the Deb's student workers type it up. So it's all in Excel. So I think I don't remember who she said. Well, I don't think she said Chloe, but I don't know.
Your email says Madeline.
That says Madeline. There you go. So, anyway, I will say that if there's inaccuracies in it, it's not my fault. I didn't type it. All right. So, before we get to the data, though, we need to get some setup of things. So what we're doing today is talking about whether or not a particular probability distribution is a good model for data that you have. So we've seen a lot of examples where the problems say this particular scenario can be modeled by a Poisson distribution with mean of 3, or this particular distribution is normally distributed with this mean and this variance. Whatever. You're always given a particular setup and say, oh, by the way, here's what the distribution's assumed to be. Of course, in real life, you don't get the luxury of being, oh, I can just assume it's this and go on with whatever you're trying to calculate. You need to make sure that whatever data you have, whatever data you've collected, actually is well modeled by whatever distribution you're trying to say models it. So what we're going to talk about today is how can you do tests of how good a model is for how good a probability distribution models the data that you have. Okay. So that's what this section 8.1 is about, is using a chi-squared distribution to conduct hypothesis tests on whether or not the model you have chosen is a reasonable one to model the scenario. Okay, so that's what we're going to do here. So unlike other hypothesis testing that we've been doing, where we are looking for small p-values and can reject the null hypothesis, in this case, we actually want larger p-values that say that, hey, by the way, our null hypothesis, our assumption that this particular distribution is a good assumption, we want high p-values to say, oh, there's a high probability that this is the right thing. Okay? So it's a little bit flipped of what we're used to. All right, so I want to go through the idea of what they talk about here in the book, just to put some things together to understand a little bit behind the scenes of what's going on, and then jump into actually doing some honest-to-goodness calculations here. All right, so we've talked about this before, of course, that if you have a binomial distribution, suppose that y is a binomial of np, we know that if np and n times, oops, it's supposed to be an n times 1 minus p are both at least 5, then we can do the central limit theorem and say that this is approximately normal on its mean and its variance. Well, what is the mean of this particular distribution? If you have a binomial with parameters of n and p, what is the mean? NP, good. And its variance? Good. And again, the reason for this is the central limit theorem, just to remind ourselves, because we talked about that earlier this semester. The reason for this is the central limit theorem. Remember, a binomial variable can be thought of as sum of Bernoulli's. Right? Your Bernoulli is just one trial with a p, with a probability of p of success. So I can think of a binomial distribution as a sum of the Bernoulli's. But we know that, I should say, sum of independent Bernoulli's. And we know the central limit theorem says that if you do enough of those sums, you get something that's approximately normal if your n's big enough, right? And for empirical purposes, n big enough just means that you've made your n so that your n times your probability of success and your n times your probability of failure both at least 5. That's a good rule of thumb to make sure that it really is approximately normally distributed. And then we know what the mean and the variance are in those cases. So this is just central limit theorem, right? So we know how to standardize this. If I look at z is equal to y minus np over square root of np times 1 minus p, that now is approximately normal on 0, 1. All we did was standardize it, right? We subtracted its mean and divided by its variance. Just trying to figure out why the dean walked by. Didn't stop here, so apparently I'm not in trouble. That's all that really matters. All right. So this is approximately normal. Now notice that the title of this section is chi-squared goodness of fit tests, right? So at some point we needed to introduce a chi-squared variable. How do we get a chi-squared variable from a standard normal? Square it, right? So this z squared is chi-square of 1, right? Yeah, I should say approximately. All of this is approximately. I don't have an honest to goodness standard normal variable because I didn't have an honest to goodness standard normal or a normal distribution. We had a binomial. We said it was approximately normal. All right, so this is approximately chi-square of 1. All right. Notice, pardon me, that we have this y here is subtracting off its expected value. So we've got, if we can think about this from this perspective, we've got this observation minus its expected value on the top. Okay? We can play around with this and actually split our chi-square variable here into 2 pieces, and let's see how that works. So your book refers to this as q. I don't honestly know why for q, except it kind of sounds like chi, I guess. I don't know. Your q is your z squared. This is going to be y minus np over np times 1 minus p. Squared on top, sorry. Now notice that your denominator part here is written in terms of essentially successes and failures, right? So what we're going to try to do here is split this into 2 pieces. One piece that just has to deal with successes, and one piece that just has to deal with failures. Okay? So to do that, the first thing we're going to notice is that we can do a little bit of like a partial fractions idea here. If you check the algebra, we get that. It's easier to check, or easier to see that if you just get a common denominator, you get this. Okay. Notice that if I multiply this first one by 1 minus p and this one by p, you've got a minus p and a plus p that'll cancel when you combine the fractions and get back to where you started. It's not unlike what we were doing with partial fractions. Now, one of the reasons why we want to do this, I just told you we're trying to split this into a success part and a failure part. Okay? This now is a success part. Right? We've got y is number of successes. So I've got successes minus expected value of successes over expected value of successes. It's almost like a relative change. There's a squared on top, but it's almost like a relative change, right? Okay. You've got observed minus expected divided by expected. There's a square in there, but it's like that, right? So what we want to do here is see if we can do the same thing for failures. Okay? Well, if you know the number of trials is n, and you know the number of successes is y, how many failures do you have? N minus y, right? So in this second term here, notice that you've got, if I just concentrate on the second term, y minus np squared over n times 1 minus p. If I add and subtract n in the top, let me do it this way, n minus y minus n, it's np squared. Did I just see, what did I do? Let's see. That's right. Plus, say it again. Oh, that's my problem. That's a plus, yes. That's my problem. Thank you. That was the issue I was having. I wasn't getting the algebra to work right. Thank you. It's n plus y. All right. If we look at these two pieces together, so the y minus n together and the n times 1 minus p together. So this is going to be what? N times 1 minus p. Right? Then I can write this as minus n minus y squared over n times 1 minus p. All right, I just factor the ones I have arrows over, I just factored out the n. Okay. Now, it's written backward, which is why I had the issue with the plus y to start with, because I want it written the other way, which I can get to here in a second. But you just told me that n minus y is number of failures, right? What is this computation right here? This is observed number of failures. What is this? Expected number of failures, right? And what are we dividing by? Expected number of failures again, right? Again, it looks like a relative change idea, doesn't it? And notice that this is reverse, right? It looks the reverse of what we have in that first term, but we're squaring it. Does the order here matter if we're squaring it? No, so I can rewrite that. So this q now becomes y minus np squared over np. plus n minus y minus n times 1 minus p squared over n times 1 minus p. Now your book uses y1 and y2, but this is where this comes from. We've got observations minus expected number of observations squared divided by expected number of observations. And same here, right? This is, we haven't done anything except for algebra. This is still approximately chi-squared of 1. Oops. Right? Now it looks like we've got two terms. It looks like we're trying to add two variables together. But remember, all we did was algebra and split it apart. It's still that same z squared we started with. So we still only have the 1 degree of freedom. And that kind of makes sense, right? There's not 2 degrees of freedom here, because y and n minus y are related to each other. Right? We're not getting an extra degree of freedom by these two terms being here, because the second term certainly depends on the first one. Okay? So we're not getting an extra degree of freedom here at all. So, in particular, when we expand this to more successes, and I'm not going to call them successes after this, but we expand this to more successes and we write out more categories, if you will, the final category is going to be basically predetermined by the previous categories. It's going to be what's left over. Okay? So for example, if you've got an urn full of blue and green and red balls, and you're looking for the distribution of blue and green and red in your sample, well, if you know how many blues and how many greens you have, you automatically know how many reds you have, because it has to fill in the rest. Right? So if I divide that into 3 categories, I only have 2 degrees of freedom, because the third one's completely determined. Right? I can pick blues and I can pick greens, but once I pick blues and greens, the red's determined. So I don't get that 3rd degree of freedom, I only get 2. Does that make sense? All right. So how does this get used? Well, let's see if we can do this. Let's look at, let's just look at the very, very first problem. This is going to extend on this idea, but let's look at the very, very first problem. The very, very first problem says that there is a 1-pound bag of candy, and since it says candy-coated chocolate-covered peanuts, I'm going to take a wild guess and say it's M&M peanut. Okay. There's brown, orange, green, and yellow. All right, so there's 224. This is 8.1-1, by the way. There's 224 pieces. There are 42 brown. There are 64 orange. There are 53 green. And there are 65 yellow. So this is the idea that I just mentioned before, that if we're going to pick out, in this case, candy, and there's 4 different possibilities, once I know how many brown, once I know how many orange, once I know how many green, I automatically know how many yellow. Right? So when we do this with a chi-squared goodness of fit test, it's good. We're going to compare it to chi-square of 3. It's going to be chi-square of 3 degrees of freedom, not 4. Okay? Does that make sense? Okay. So in this particular case, we're going to split this up into 4 categories. So it's going to look a lot like this, where we only had the 2 categories. But you can go through, they go through it in the book, which is why I'm not going to spend a lot of time doing it. You can go through, and the Q variable you can think of as your first class, you've got a number of observations that's in your first class, expected value that's in your first class, divided by the expected value of your first class. And you can break this up now into 4 classes. So again, the idea here is that this is approximately chi-square of 3. And this is how we're going to compute our test statistic. Actually doing this is going to be our test statistic, and then we're going to compare it to our critical value. All right, so let's see how we do this. Let's do this in Excel, just so that we can see how I'd like to do it in Excel here. There we go. All right, so in this case we had, already flipped the page, we had 42 brown, it was a brown, orange, green, and yellow. $42 brown, and there was 64 orange, there was 53 green, and there was 65 yellow. All right, so the hypothesis in this case is that the colors are evenly distributed. That is our hypothesis that we want to test. There's an equal number, or overall, there's an equal chance that each color was chosen before put in the bag. Okay? That's the hypothesis. If that's the case, what's each of our P1 through P4 going to equal if there's supposed to be an equal chance of each color being selected before it's put in the bag? 1/4, right? If it's going to be equal. So our null hypothesis here is that P1, P2, P3, and P4 are all the same. So this first column in Excel here, let me zoom in a little bit so we can see it. Our first column in Excel here is our observed values, right? These are our observed values. We should be able to get our expected values then by doing what? Well, we know the total number was 224, and we know the probability for each is 1/4, right? So your expecteds here should just be, pardon me, the 224 divided by 4, right? So they all should be 56. So again, just to emphasize this, let me just put in a row. This was our observed, and this is our expected. Now, as far as the statistic goes, what do we want to do with the observed and the expected? What did our statistic look like? What did the formula look like that we wrote down? Yeah, good. Observed minus expected and then square it, but over expected, right? So in this one, I want to do observed minus expected And I'll just square it so we actually see it, and then I'll do the divided by. Okay. So there's our observed minus expected squared. If I can spell. All right. And then in the next column, we'll just do the division. So we'll do observed minus expected squared and divided by expected. So that's the D2 divided by the C2 here. Okay for me to enter. And copy it down. So this is, oops. Oh, I'm just going to write, I don't know what I'm going to write. I don't want to write a big long descriptor, but division. Does it work? I'm just trying to give a header for it. It doesn't really matter. What do we want to do with all of those divisions, all those quotients? Add them. So we get 6.25. Now, again, if we're going to do this at whatever level, it doesn't really matter. We need to compute, or if we were going to do it with the table, we would need to look the number up in the table, right? And we would look up chi-square 3 on, say, at 0.05 and see if we're bigger than that, okay? Or we can do this in Excel. Say I want to do the chi-squared distribution right tail probability. So that second one, the chi-square dist, it's chi-sq.dist.ert. Because that looks like something you're supposed to pronounce. Chi-squid-discert. Anyway, if I do that one, it wants the x value and the degrees of freedom. So if I just go up and grab that x value that the chi-square statistic that we computed, and then degrees of freedom is 3 in this case. You get 0.1-ish. This would be your p-value of the test. So even we wouldn't necessarily reject the null hypothesis unless we're willing to do at a significance level a little bit bigger than 0.1. But there's not a lot of evidence here saying that this is a good fit. Okay? Remember, if it's going to be a good fit, we want higher p-values. Right? That's the whole point of doing this. As a young budding actuary, if you're trying to figure out a way to model probabilities based on data that you have observed in the field, then you want to try to come up with a probability distribution that seems to fit your data that has a likelihood of fitting it well. Okay? That's kind of like when you've done regression analysis. If you've done regression analysis before, you want that higher R-squared value, because the R-squared is a way to tell you the amount of error that's explained by the model. We talked just a smidge about R-squared last semester too, but that's what the R-squared tells you. The 1 minus the correlation coefficients. Anyway, whatever, it doesn't matter. When you do that R-squared value, that tells you the amount of error that's explained by the model. So if it's perfectly correlated, then your R-squared would be 1. Perfectly correlated, whether it's positive or negative. It's the same idea. You want that high R-squared. So in this case, you want a high p-value. It has a high probability of being accurate. Right? Does that make sense? So we did this with binomial. So let's do another one. Let's look at 8.1-2. Same idea. In 8.1-2, they have same idea. They have M&Ms, of course. But in this case, we're going to have 5 colors. With the following null hypothesis. One of the colors is much more likely than the others, and 2 of them are the same, and they're double the other 2. So, just to tell you what the colors are, the first one is brown, the second one is yellow, the third one is orange. I could spell the word orange, that would be helpful. The fourth one is green. And the fifth one is coffee. I don't think I would call it tan, but sure, coffee, why not? All right, so then the observations here are 224, 119, 130, 48, and 59. All right, so we're going to do the same thing. Brown, yellow, orange, green, coffee. All right, 224, 119, 130, 48, 59. All right, so they told you it was a total of 500 M&Ms. If the first one has probability of 0.4, what should I type in cell C2? Because we're going to do expected value now. If there's a total of 500 candies, what should I type in C2? You mean times, right?
Yeah.
All right, so that'd be the 200, right? The next one would be 500 divided by, or not divided by, you got me saying it now, times 0.2. And that'll be the same one here. So I'm just going to just retype it because I just need the number, right? Then the next one will be, it's half of that, so it better be 50 in each of those. All right. What do we calculate next? I mean, you can actually do it all at once if you really wanted to. Yeah, the difference squared. So observed minus expected squared. And if you really wanted to divide by expected at that time, you could. You could do it all in one step. I personally just like to see what's going on. But you could have done the divides by the expected here in this column, right? You could do it all in the same formula. And now we'll divide by the expected. So I want to do this one divided by this one. Get those. Is that okay? Everybody agree? If you're typing along, do you agree with those numbers? What do we do with all of those numbers now? Sum it? That's a pretty big chi-squared value. So it looks like looking like this is not a good model. Okay. So if we want to check a p-value from Excel, I can do that chi-squared right-tailed test again. Or right distribution right-tail, sorry. And then I pick the chi-squared statistic we just computed. How many degrees of freedom do we have in this particular case? Yeah, 4, right? That p-value is low. So we would reject the null hypothesis, so this is not a good fit. Does that make sense? See how we can use some data here. See, I have an email from my insurance agent since we bought a car over the weekend. All right, so this should be the data for number 3, 8.1-3. And I'll make sure that, well, it's all the problems in this particular section where there's data I had are typing all in. So if I give you over homework, you should already have it typed into Excel, so you don't have to do it. Especially with some of these, there's a lot of numbers in there. Again, I can't verify its accuracy, but it doesn't matter where you're going to go off the numbers anyway. It doesn't really matter. Okay. It's a matter of getting the experience. Okay. So in this particular case, it says that the Michigan Daily Lottery, at least at the time when this book was written, generates a 3-digit number. And it should be the case that each digit is equally likely to be selected because it's being generated one at a time. So in this particular case, we want to test if the probability really is 1/10 for each digit being chosen. Okay. So one of the things that we can do here, this is our observations. I want to use Excel to count this stuff. And I don't want to count it myself. All right. So let's just let me put in the numbers 0 through 9 here. So I just typed 0 and 1 and then copied it down, and it recognizes the pattern. It's a nice thing about Excel and an annoying thing about Excel. Sometimes you just want to copy the same thing down multiple times, and it says, oh, you have this pattern. Just start changing everything. It can be a pain. Anyway, so what I want to do is use what's referred to as the COUNTIF function. So that's the if I just type the word count, it's the fourth one down. COUNTIF. I'm going to highlight the block of stuff here. Ooh, maybe. Highlight the block of stuff. Now, I want to be able to use this and copy it down. So I don't want the block, I don't want that array to change as I go, so I'm going to use absolute cell references. So let's use function F4 to change those to absolute cell references when I copy it down. This function F4 will put the dollar signs in front. So you don't have to type the dollar signs yourself. Isn't that a nice little trick?
Yeah. This whole time, even in numerical, I was like hitting F1. I wanted to do it, but I didn't.
You always don't. Yeah, that's why I won't do it. Yeah.
So the whole time I just been typing it.
The best thing about it is, Annika, it even cycles. If you hit it over again, it'll change it from. If you click it again, it'll take it off the column, I think. If you click it again, it'll take it off the row. And if you click it again, it'll go back to where you started. Yeah, I know. It cycles it around. Didn't learn that in Miracle?
No.
Yeah, we'll see. That's okay. You don't want to be in my numerical class this semester. Disaster is about the only word I can think of to describe the last week. It's fine. Whatever.
You sure?
Am I sure? No. It's just more frustrating than anything. All right. So then I want to count how many zeros there are. So I just want to compare it to the 0 that we put in the previous cell. If you can't tell, it does bug me a little bit. And then we'll just copy it down. So there's the observed number in each of them. And now we didn't have to go count them ourselves. Excel is a wonderful tool for doing computational things. Except when solving doesn't work on that. All right. So then this is our observed columns, and the next one's going to be expected. Well, if you've got 50 observations, and each time it should be a 10th, what should be the expected number for each of them? If there were 50 total observations, and it's a probability of a 10th for each of them, what should be the expected value? 5 for each of them. Good. So this column just needs to be 5 all the way down. I don't need to do any fancy calculation for that. Oh, hey. I didn't do anything. It did it by itself. That was weird. I must have hit some button. I didn't do anything. I just was starting to get ready to pull it down, and it just copied it all the way down. I did not like that.
The bottom where says like the average count and some TTC.
Oh, down here? Yeah, this is the. You can actually go in there and set what you wanted to see.
Oh, I'm sorry, I don't see that one.
Yeah. I don't know. I wouldn't know how to do it on the Mac anyway, probably. Yeah, but you can actually change what those are at the bottom. And so if you just want to see what the sum is and not have to type sum every time, you can just highlight it and then it'll the sum or the average or whatever. If that's all you're trying to do.
Oh, mine does do it.
Yours does.
It wasn't highlighted.
All right. So we want to do observed minus expected. I'm just going to do it all at once this time. Squared and then divided by expected. Just to save time, I'll do it all at once. I'm sorry, I didn't zoom in, did I? Did everybody get those numbers? All right, so let's sum that up. And then let's do our chi-squared. How many degrees of freedom do we have this time? How many? 9, right? Because there's 10 digits. All right. So that gives our p-value. That's fairly high, right? There's certainly not enough evidence to reject that they're not equally likely. And there's only 50 observations, too. So when your expected value is only 5 for each of them, remember that's kind of the minimum we like for normal to get the chi-square to begin with. In general, at least as a rule of thumb, you would like those expected values, especially if you're doing things with binomial, you want those expected values all to be at 5 or bigger. Now again, if you're doing different types of distributions, if it starts to tail off, then you would want those expected values to tail off as well. So, this one okay? Yeah. What do you mean? Okay, so what what we're doing here is the reason why there's 9 degrees of freedom is because we've got 10 categories. You can think of this last one as being the failures part. It's gathering what's left over. Yeah, so if it's not 0 through 8, then it had to be a 9. So it's the last category that gathers your failures, which is why you don't have that degree of freedom there. That's the idea. All right, so what we'll talk about next time with these goodness of fit tests is how would you see if a Poisson's a good fit or a normal distribution is a good fit. And again, in that case, what we'll do is we'll still look at the observations, and we'll just look at the corresponding probabilities of seeing those observations using those distributions and seeing if the expected values work. Okay. So it's not a big deal. We just have to do some extra computations, but that's what Excel's for. So it'll make it pretty easy. All right. Yeah. Computation will be pretty easy, we should say. All right. So we'll do that next time. We'll probably get into section 8.2 as well, which talks about contingency tables, which again will be more chi-squared tests. So, all right. We'll see you Wednesday.